What if everything we thought we knew about the universe was about to flip upside down? Picture this. After 13.8 billion years of unstoppable growth, the cosmos suddenly hits the brakes. Galaxies slow their frantic rush apart. Distant stars begin inching closer. Space itself, once stretching endlessly outward, starts curling back in like a deflating balloon. This isn't science fiction, it's a real possibility some scientists call the Great Expansion Reversal, and it could rewrite the fate of everything. Right now, our universe is expanding faster than ever, propelled by a mysterious force we call dark energy. But what if that force isn't constant? What if one day it weakens or worse, reverses? The consequences would be unimaginable. Galaxies would collide in a cosmic traffic jam of epic proportions. Stars would be torn apart as space contracts around them. Even time itself could unravel in ways we can barely comprehend. This isn't just theoretical physics, it's a question that cuts to the heart of existence. Are we living in a universe with an expiration date? Today, we're embarking on a journey to the edge of known science, where the rules of reality bend and the future of the cosmos hangs in the balance. We'll explore cutting-edge research that suggests the unthinkable, that dark energy might not be the universe's final word. We'll dive into competing theories, from cosmic collapse scenarios to mind-bending models where multiple universes bounce between expansion and contraction. And we'll ask the haunting question astronomers are only beginning to grapple with. If the universe can expand, what's stopping it from shrinking? Strap in, this isn't just a story about distant galaxies. It's about the ultimate fate of every atom, every planet, and every one of us. The answer might be closer and more terrifying than we ever imagined. For nearly a century, astronomers have watched the universe stretch itself thinner with each passing moment. Edwin Hubble first noticed it in the 1920s, the eerie red glow of distant galaxies. Their light stretched into longer wavelengths as they raced away from us. This wasn't just a few stars drifting apart. It was space itself expanding, carrying galaxies along like raisins in an inflating loaf of bread. Today, we know this expansion isn't just continuing, it's speeding up, thanks to an invisible puppet master called dark energy. But here's where things get unsettling. What if dark energy is playing a trick on us? For decades, scientists assumed dark energy was a constant force, woven into the fabric of space itself. But new data hints it might be far more fickle. Imagine blowing up a balloon with a slow leak. At first, it expands rapidly, but as the air escapes, the growth stalls. Now picture that balloon is the entire cosmos, and the leak is dark energy losing its strength. Recent telescope observations have spotted subtle wrinkles in this cosmic acceleration, tiny deviations from the expected rate. Some researchers think these could be the first tremors of a coming reversal, like a roller coaster pausing at its peak before plunging backward. The stakes couldn't be higher. If dark energy weakens enough, gravity, the universe's relentless glue, could gain the upper hand. Galaxies would stop fleeing from one another and begin a slow-motion collapse. But here's the twist. We don't know if this contraction would mirror the Big Bang in reverse, or if it would unleash something entirely stranger. Some theories suggest space might crumple like a piece of paper, while others propose it could trigger a new Big Bang, recycling the universe in an endless cycle. One thing's certain, if the expansion reverses, the universe we know won't just change, it will vanish, rewritten by forces we're only beginning to understand. So what could flip the switch? The answer might lie in the quantum realm, where particles flicker in and out of existence. Some physicists speculate that dark energy isn't a static force but a field that could decay, like radioactive material slowly losing its potency. Others propose it's entangled with hidden dimensions, and a shift in those unseen layers could send our universe careening toward collapse, the scariest part. If this reversal has already begun, we might not notice until it's too late. The universe's scales tip slowly, over billions of years, and by the time distant galaxies start blue-shifting, hurtling back toward us, the countdown to cosmic doom could already be halfway finished. This isn't just about galaxies and empty space, it's about the atoms in your body, the light from your screen, and the very laws of physics holding reality together. If the expansion reverses, the universe won't just shrink, it will unravel. Time could flow backward, matter might disintegrate into pure energy, and the cosmos could rewrite its own rulebook. The unsettling truth, we're cosmic detectives piecing together a crime scene 13.8 billion years in the making, and the clues keep changing. The universe's fate isn't written in stone. It's written in dark energy's invisible ink, and we're just learning how to read it. Dark energy is the mysterious architect shaping our universe's destiny, an invisible hand stretching spacetime itself. Imagine it as the anti-gravity, a force so dominant it makes up nearly 70% of the cosmos's energy budget. For billions of years, it's been winning a cosmic tug of war against gravity, flinging galaxies apart faster and faster. But what if this force isn't as steadfast as we think? Hidden in the fine print of the universe's behavior, there are whispers of something unsettling. Dark energy might not be permanent. Some of the boldest theories in physics suggest dark energy could decay, like a battery slowly losing its charge. Picture a sprinter who starts a race at full speed but begins to tire mile after mile. If dark energy weakens over time, gravity, the universe's oldest and most patient force, could stage a comeback. Galaxies drifting apart would first slow their retreat, then stop entirely, like cars coasting to a halt on an empty highway. But gravity doesn't just stop, it pulls, and if it regains control, those galaxies wouldn't just freeze, they'd reverse course, drawn back together in a celestial reckoning. The numbers behind this scenario are staggering. Right now, dark energy's repulsive push is about 10 to the power of 120 times weaker than the theoretical maximum it could reach. That's a 1 followed by 120 zeros, a number so large it defies everyday comprehension. Yet even a tiny shift in this balance could tip the scales. Some models suggest dark energy might be a temporary phase, a cosmic pressure that fades as the universe ages. Others propose it's entangled with quantum fields we don't yet understand, fields that could fluctuate or collapse without warning. The real enigma is time. If dark energy decays, it likely wouldn't happen overnight or even over millions of years. This would be a slow-motion unraveling, a transformation spanning billions of years, far too gradual for any single civilization to witness from start to finish. By the time the first galaxies begin their inward fall, humanity, if it still exists, might not even recognize the signs. The universe's grand reversal could be as subtle as a tide turning, invisible until the waves start crashing in. What's truly humbling is how little we know. Dark energy could be constant, as many physicists assume, or it could be a ticking clock counting down to a cosmic collapse. The only way to know for sure is to keep watching the skies, tracking the faintest clues in the light of distant supernova and the large-scale structure of the universe itself. Every new telescope, every deeper observation brings us closer to answering the ultimate question. Is the universe's expansion a one-way trip, or are we riding the crest of a wave that will one day come crashing back? Gravity has been the quiet underdog in this cosmic battle, biding its time while dark energy steals the spotlight. Think of it like a rubber band stretched to its limit. The further galaxies drift apart, the stronger gravity's pull becomes, waiting for the moment it can snap everything back. If dark energy's dominance ever wanes, gravity wouldn't just gently take over. It would stage a spectacular comeback, rewriting the universe's trajectory in a process scientists call the Big Crunch. Picture the Big Bang played in reverse, galaxies hurtling toward each other, stars colliding in fiery mergers, and space itself shrinking like a deflated balloon until all matter collapses into a single, unfathomably dense point. But how realistic is this scenario? The evidence is tantalizing but fragmented. On one hand, we know gravity's influence grows stronger as objects get closer together, just as Earth's pull is fiercer on a skydiver than on a satellite. If expansion slows enough, gravity could indeed become the universe's dominant force again. Some models even suggest this collapse wouldn't be uniform. Imagine patches of space crumpling like foil while others hold their shape, creating a chaotic mosaic of contracting regions. Yet there's a counter-argument. Dark energy's acceleration might be too relentless, like a car with a stuck gas pedal, leaving gravity forever chasing its tail. The Big Crunch isn't the only possibility, though. Some theorists propose a stranger twist, a big bounce. Instead of collapsing into oblivion, the universe might rebound like a cosmic phoenix, with the crunch birthing a new Big Bang. It's a cyclical vision where expansion and contraction repeat in an endless loop, each cycle rewriting the laws of physics. Others warn of a darker outcome, a big rip where dark energy grows so strong it shreds galaxies, stars, and even atoms before contraction ever begins. The truth might lie in the subtle behavior of distant supernova, whose light holds clues about whether expansion is truly unstoppable or if gravity is quietly gaining ground. What's chilling is the timescale. If contraction began today, the first signs would be subtle, a slight dimming of faraway galaxies, a faint blue shift in their light. But over billions of years, the sky would transform. Constellations would melt together as stars creep closer, and the cosmic microwave background, the afterglow of the Big Bang, would warm from its icy -270 degrees Celsius as space compresses. By the final moments, the night sky would blaze with colliding galaxies, their light blue shifted into invisibility as the universe rushes toward its fiery end. Yet for all the drama of the Big Crunch, it's still just one hypothesis among many. Some researchers argue that dark energy's properties make reversal impossible, locking the universe into eternal expansion. Others believe quantum fluctuations or undiscovered dimensions could rewrite the rules entirely. The only certainty, gravity hasn't surrendered yet. It's the silent force sculpting galaxies today, and if the cosmic tides turn, it could be the hand that pulls the universe closed. The question isn't just whether gravity will win, it's whether we'll live in a universe that lets it. The Big Crunch theory paints a picture of the universe not with a whimper, but with a spectacular collapse. Imagine the night sky growing brighter over billions of years as galaxies crowd together, their light blue shifting into higher energies. Stars that once drifted apart would now slam into each other like marbles in a shrinking box, triggering waves of supernova. Space itself would grow hotter, not from the warmth of starlight, but from the sheer compression of matter and energy, eventually reaching temperatures so extreme that atoms themselves would disintegrate. This isn't just an ending, it's the universe folding in on itself, reversing the very expansion that began with the Big Bang. For decades, the Big Crunch was the leading contender for the universe's ultimate fate. Einstein's equations hinted at it, showing how gravity could eventually overcome cosmic expansion if the density of matter was high enough. Even the steady-state theory, which proposed an eternal universe, couldn't escape the gravitational tug of war at its core. But then came the bombshell discovery of the late 1990s. Dark energy wasn't just real, it was accelerating the universe's expansion. Suddenly, the Big Crunch seemed like a relic of outdated physics, a cosmic doomsday scenario shelved by new evidence. Yet science rarely discards ideas completely. Recent models have breathed new life into the crunch, albeit with twists. One compelling variant suggests the universe isn't on a one-way trip to oblivion, but part of an endless cycle: expand, contract, rebound, repeat. Think of it like a cosmic heartbeat, each pulse birthing a new universe from the ashes of the old. This Big Bounce theory sidesteps the problem of dark energy by proposing it's not a constant force, but a phase that eventually exhausts itself, allowing gravity to reset the clock. Some versions even suggest quantum effects could prevent total collapse, leaving just enough space for a new Big Bang to ignite. The math behind these ideas is staggering. In cyclic models, the universe might contract until it reaches a density 1 trillion times greater than a neutron star, then rebound with laws of physics subtly rewritten. String theory adds another layer, proposing hidden dimensions that could warp gravity's influence, making contraction possible even amid dark energy's push. Skeptics point out gaps. If dark energy truly dominates, gravity may never get its chance. But supporters counter that we've barely scratched the surface of dark energy's behavior. What if it's decaying or interacting with undiscovered particles? Here's the haunting part. If the Big Crunch is real, it might already be underway. The first signs would be invisible to us. Galaxies so distant their light hasn't reached us yet might already be slowing, preparing to reverse course. By the time nearby stars show blue shift, the collapse would be unstoppable. Yet even this grim scenario offers a strange comfort. In a cyclic universe, every ending is just a prelude to another beginning. The atoms in your body, forged in stellar furnaces, might one day fuel a new cosmos. The question isn't just whether the universe will crunch, it's whether we're living in the first chapter or the latest in an infinite series. While the Big Crunch offers a dramatic vision of cosmic collapse, it's far from the only fate on the table. Some scientists argue the universe isn't headed for a reunion, it's on track for a brutal divorce. Enter the Big Rip, a scenario so violent it makes the crunch seem almost gentle. Picture dark energy growing stronger over time, not weaker, until its repulsive force overpowers even the bonds holding atoms together. Galaxies wouldn't just drift apart, they'd be shredded. Stars would unravel mid-orbit, planets would disintegrate, and in the final moments, space itself would stretch so thin that quarks, the fundamental building blocks of matter, would be torn from each other in a catastrophic crescendo of dissolution. The math behind the Big Rip is as chilling as it is elegant. If dark energy's strength increases, a property theorists call phantom energy, it could accelerate expansion exponentially. Unlike the gradual slowdown of a potential reversal, this would be an unstoppable runaway train. Current estimates suggest that if phantom energy is real, the end could come shockingly fast within 22 billion years, a blink in cosmic terms. First, galaxy clusters would be ripped apart, then individual galaxies, then solar systems. In the last gruesome hour, stars and planets would explode as the forces binding them disintegrated. Even black holes, the universe's most resilient objects, might evaporate as space stretches beyond their ability to maintain cohesion. Yet not all scientists buy this apocalyptic vision. A rival camp argues the universe won't tear itself apart, it'll simply fade away. The Big Freeze or heat death presents a quieter but no less final destiny. Here, dark energy remains constant and expansion continues indefinitely. Over trillions of years, galaxies would drift so far apart that their light could never reach one another. Stars would burn out one by one until the last red dwarf flickers into darkness. black holes would slowly evaporate via Hawking radiation, leaving behind a vast, featureless void where temperatures approach absolute zero. No explosions, no fireworks, just an endless, silent drift into darkness. Which scenario holds more weight? Observations of distant supernova currently favor the Big Freeze, as dark energy's acceleration appears steady for now. But the margin is razor-thin. Subtle deviations in data could tilt the scales toward the rip or even revive the crunch. Some theorists propose a middle path, quintessence, a form of dark energy that fluctuates over time, potentially avoiding all three extremes. Others suggest these fates might be local, with different regions of the universe meeting different ends based on unseen variables. The stakes of this debate go beyond theoretical physics. If the Big Rip is real, it could happen sooner than we think, well before the sun dies. The Big Freeze offers more time but a far lonelier conclusion. And lurking beneath it all is a humbling truth. We're deciphering the universe's fate using less than 5% of its total matter and energy. The remaining 95%, dark matter and dark energy, remain mysteries, their long-term behavior still anyone's guess. Until we crack those enigmas, the universe's final act will stay as uncertain as it is inevitable. At the heart of quantum mechanics lies a bizarre truth: empty space is never truly empty. Even in the deepest void between galaxies, the fabric of reality crackles with energy. Particles and antiparticles flicker into existence for fleeting moments before annihilating each other, a phenomenon known as quantum fluctuations. This isn't just theoretical, it's been measured in labs, with real effects like the Casimir force, where two metal plates in a vacuum are subtly pushed together by these ghostly particles. But here's where things get unsettling. What if this quantum foam isn't stable? What if, somewhere in the universe, a single fluctuation tips the balance, creating a bubble of fundamentally different physics that expands at the speed of light, erasing everything in its path? That's the nightmare scenario called vacuum decay. Think of the universe's current state like a ball resting in a valley, a stable, low-energy position. But quantum theory suggests there might be a deeper valley, a truer vacuum state with even lower energy. If something knocks the ball over the hill, a random quantum event, a high-energy collision, it could start rolling downhill, rewriting the laws of physics as it goes. This new vacuum state wouldn't just change particles or forces, it could alter the speed of light, the strength of gravity, even the nature of time itself. The shockwave would spread unstoppably, a cosmic reboot propagating faster than any warning signal could travel. By the time we saw it coming, it would already be here. The math behind this is both precise and terrifying. Calculations suggest the new vacuum bubble would expand at nearly light speed, transforming everything it touches. Atoms might unravel, their electrons vanishing into rewritten quantum fields, the fundamental constants that make life possible, like the fine structure constant governing electromagnetism, could shift, rendering chemistry itself impossible. Even space-time might fracture, creating regions where causality breaks down. The chilling part, this could already be happening somewhere in the cosmos. A single quantum event in a distant galaxy could have triggered a bubble centuries ago, and its lethal frontier might be rushing toward us right now, invisible until the moment it arrives. Yet there's a twist to this apocalyptic scenario. Some theorists argue vacuum decay might not be an end, but a transformation. A new vacuum state could birth a universe with entirely different physics, one where stars, planets, and even life might re-emerge under unfamiliar rules. It's a cosmic lottery. Would the new laws allow complexity, or would they produce a barren, featureless void? We have no way to predict because, by definition, the rules after vacuum decay are beyond our current physics. The odds of this happening are astronomically low, but not zero. Particle colliders like the Large Hadron Collider briefly create energies that could, in theory, nudge the vacuum toward instability. Thankfully, every experiment so far suggests we're safe. Natural cosmic rays have bombarded Earth with far higher energies for billions of years without triggering catastrophe. But the deeper question remains, is our universe sitting on a quantum knife edge? Or is this just one of many possible doomsdays we've yet to uncover? The answer might lie in the very fabric of reality, and whether that fabric is as sturdy as it seems. The cosmic microwave background is like the universe's baby picture, a faint glow of light from just 380,000 years after the Big Bang, frozen in time and stretched into microwaves over billions of years of expansion. But this ancient afterglow isn't just a relic, it's a treasure map encoding secrets about the cosmos's past, present, and even its ultimate fate. Embedded in its subtle temperature variations are clues about how matter clumped together in the early universe, setting the stage for everything that followed. And now, astronomers are spotting something odd in these patterns, tiny irregularities that might be the first whispers of a future collapse. Take a closer look at the CMB, and you'll see it's not perfectly uniform. It's speckled with hot and cold spots, some slightly warmer or cooler than the average -270 degrees Celsius. These fluctuations are cosmic breadcrumbs, showing where matter was slightly denser or sparser in the infant universe. Over eons, gravity amplified those tiny differences, sculpting them into galaxies and galaxy clusters. But here's the twist: the exact shape of these fluctuations could reveal whether dark energy's grip is permanent or slipping. Recent high-precision measurements from telescopes like Planck and the Atacama Cosmology Telescope have detected anomalies, subtle asymmetries and unexpected alignments in the CMB's patterns that don't quite fit the standard model of eternal expansion. Some researchers think these deviations could hint at an impending reversal. Imagine blowing up a balloon with faint creases. If you let the air out slowly, those creases might realign in predictable ways. Similarly, if dark energy weakens and contraction begins, the CMB's fluctuations could carry faint echoes of that shift. One tantalizing clue comes from the so-called cold spot, a mysterious region of the CMB significantly cooler than its surroundings. Could this be a cosmic bruise, evidence of an earlier collision with another universe in a multiverse scenario? Or is it a signpost marking where gravity is already beginning to reassert itself? Skeptics argue these anomalies might just be statistical flukes, cosmic static in an otherwise predictable signal. The stakes of this debate are enormous. If the CMB's quirks are real, they could rewrite our understanding of dark energy's nature. Perhaps it's not a constant force but a dynamic field evolving over time, like a river slowing as it nears the sea. Or maybe the universe's geometry isn't perfectly flat as we've assumed, but subtly curved, a shape that could allow gravity to eventually win out. The answers might lie in next-generation observatories like the Simons Observatory or the upcoming Light-Bird satellite, which will map the CMB with unprecedented precision, hunting for the faintest hints of a universe preparing to turn inward. For now, the CMB remains a cryptic message from the dawn of time, its full meaning just beyond our grasp. But every new measurement brings us closer to deciphering whether the universe's expansion is a one-way journey, or if the cosmos is quietly counting down to a reversal we can't yet see. One thing's certain, the universe's oldest light still has stories to tell, and they might be darker and stranger than we ever imagined. Dark matter is the universe's silent architect, an invisible scaffold shaping the cosmos from the shadows. While dark energy steals headlines for pushing galaxies apart, dark matter works quietly in the background, its gravitational pull weaving the cosmic web that binds everything together. Picture a vast, unseen network stretching across billions of light years, with galaxies clinging to its threads like dew on a spider's web. This mysterious substance makes up 27% of the universe's total mass energy, yet it refuses to interact with light, revealing itself only through its relentless tug on stars and galaxies. But what happens if dark energy's dominance fades? Dark matter could step into the spotlight, becoming the gravitational heavyweight that pulls the universe back from the brink of endless expansion. Simulations of cosmic collapse paint a dramatic picture. Without dark energy's repulsive push, dark matter's gravity would begin drawing galaxies together in a slow-motion reunion. Supercomputer models show halos of dark matter, those invisible cocoons surrounding galaxies merging like droplets of water on a window pane. As these halos collide, they drag ordinary matter along for the ride, triggering waves of star formation and catastrophic galactic mergers. The process wouldn't be uniform, though. Dense regions of dark matter would collapse faster, creating pockets of extreme gravity where space itself might warp unpredictably. Imagine throwing a handful of marbles onto a rubber sheet. Some would roll together quickly, while others linger at the edges. The universe's contraction could be just as uneven, with some galaxies rushing toward oblivion while others hold out in isolated pockets. But here's the twist. Dark matter might not just accelerate collapse, it could dictate how the universe crumbles. Some theories suggest dark matter particles could interact with each other in ways we don't yet understand, perhaps through hidden forces or quantum effects. If these interactions release energy, they might slow the contraction, turning a fiery big crunch into a more gradual cosmic sigh. Others propose dark matter could decay over time, its gravitational grip weakening just as it's needed most. The scariest possibility, dark matter's distribution might already be seeding the universe's demise. Vast filaments of dark matter stretch between galaxy clusters like cosmic highways, and if contraction begins, these highways could become gravity's express lanes, funneling matter toward unimaginably dense knots. The key to unraveling this mystery lies in the shadows, literally. Astronomers are racing to map dark matter's hidden architecture using techniques like gravitational lensing, where the bending of light around massive objects reveals the invisible mass distorting spacetime. Recent observations of colliding galaxy clusters, like the famous Bullet Cluster, show dark matter parting ways with visible matter like a ghost walking through walls. These eerie separations hint at how dark matter might behave during universal contraction, whether it clumps, dissipates, or even triggers new phenomena as gravity's hold tightens. Yet for all its influence, dark matter remains frustratingly elusive. We've never directly detected a single particle of it, and its true nature could upend everything we think we know about cosmic collapse. Is it a sea of undiscovered particles or the fingerprint of extra dimensions? Could it interact with dark energy in ways that accelerate or prevent reversal? The answers might lie in the next generation of experiments, from ultra-sensitive detectors buried deep underground to space telescopes designed to probe the universe's darkest corners. One thing's certain, if the cosmos ever does reverse its expansion, dark matter won't just be a bystander. It'll be the gravitational hand that closes the book on the universe as we know it. Black holes are the universe's ultimate paradox, regions of spacetime so warped that not even light can escape their grasp. In an expanding cosmos, they lurk like cosmic predators, growing as they consume stars, gas, and even other black holes. But in a contracting universe, their role shifts from destroyers to potential creators. Picture a cosmos reversing its expansion. Galaxies crowd closer together, stellar collisions multiply, and black holes feast on the chaos, swelling in size like gluttons at a cosmic banquet. Over billions of years, these gravitational monsters would merge into ever larger behemoths. until the universe's final act might hinge on a handful of supermassive black holes spiraling toward one another in a dance of annihilation and rebirth. The math behind this scenario is both elegant and unsettling. As space contracts, matter becomes denser, feeding black holes at an accelerating rate. Simulations suggest that in the late stages of collapse, black holes could dominate the universe's mass, their event horizons stretching to swallow entire galaxies. But here's where it gets stranger. Some theories propose that these black holes might not be endpoints but gateways. Inside a black hole's crushing depths, the known laws of physics break down and space-time curves infinitely toward a singularity, a point of zero volume and infinite density. Yet some physicists, like Nobel laureate Roger Penrose, argue that singularities could be bridges to new universes, their extreme conditions birthing fresh Big Bangs. It's a concept called conformal cyclic cosmology, where each universe's death plants the seed for the next. The implications are staggering. If true, our universe might be one link in an endless chain, with black holes serving as cosmic recycling centers. Imagine a supermassive black hole, swollen to unimaginable size during the Big Crunch, collapsing into a singularity so intense it reboots spacetime itself. The energy packed into that singularity could erupt as a new inflationary epoch, spawning an entirely new cosmos with its own laws of physics. This isn't just speculation. Certain solutions to Einstein's equations allow for such a bounce, though the details remain hotly debated. Skeptics point out the lack of observable evidence, while proponents argue that the signatures of a prior universe might be hidden in the cosmic microwave background's faintest patterns. Time adds another layer of mystery. In a contracting universe, black holes wouldn't just grow, they'd warp time itself. Near an event horizon, time slows to a crawl due to relativistic effects. As collapse accelerates, this time dilation could create bizarre pockets where causality unravels. Picture two observers, one near a black hole, the other in free space. To the outsider, the universe's end might seem imminent, but to the observer near the black hole, billions of years could pass before the final moments. Some models even suggest that in the universe's last instant, all black holes might merge into a single, universe-spanning singularity, a moment where time loses all meaning, and the distinction between past, present, and future blurs into oblivion. Yet black holes might offer more than just doom. Quantum mechanics hints that information, the fundamental stuff of reality, can't truly be destroyed. Even as black holes evaporate via Hawking radiation, they might encode information about their consumed matter in subtle quantum states. If a new universe emerges from a singularity, could that information resurface like data etched into the fabric of space-time? It's a tantalizing possibility. The atoms in your body, forged in stars and perhaps swallowed by black holes, might one day re-emerge in a reborn cosmos. The universe's contraction wouldn't just be an end, it could be a cosmic reset with black holes as the architects of renewal. The interplay between black holes and cosmic collapse is more than theoretical, it's a lens into the deepest questions of existence. Are we living in a one-and-done universe, or is reality an endless cycle of death and rebirth? If black holes hold the key, the answer might lie in the very voids we once thought were final. As we peer into their abyss, we're not just studying destruction. We might be glimpsing the first whispers of a universe yet to come. Time as we know it might not survive the universe's collapse. The arrow of time, that relentless forward march from past to future, isn't just a human construct. It's woven into the fabric of reality through entropy, the universe's tendency toward disorder. Right now, entropy increases as the cosmos expands, creating the one-way flow we experience. But in a contracting universe, entropy could theoretically reverse. turning time's arrow backward like a clock running counterclockwise. Imagine shattered glass reassembling itself, flames drawing heat back into burning wood, or memories unfolding in reverse, every atom retracing its steps toward the Big Bang's singularity. This isn't just poetic speculation, it's a real debate among physicists, with Nobel laureate Roger Penrose arguing that a universe reborn through cyclical collapse might reset entropy entirely. Not everyone buys into this radical vision. Critics point out that even if space contracts, entropy might continue increasing, meaning time would still flow forward, just in a shrinking cosmos. Think of squeezing a balloon filled with confetti. The balloon gets smaller, but the confetti inside doesn't magically rearrange itself into neat stacks. Similarly, stars and galaxies might hurtle toward each other, but their collisions would still create chaos, not rewind it. The key lies in quantum gravity, a still unknown theory that could redefine how time behaves at cosmic scales. Some models suggest time itself emerges from quantum entanglement, meaning a universe reversal could unravel causality at its roots, the most unsettling possibility. Localized time reversal. As contraction accelerates, regions of intense gravity, like near black holes, might experience time differently than the wider universe. Picture a cosmic hourglass where time flows normally at the top but backward at the bottom, with the boundary between them warping reality itself. This could create zones where cause and effect invert, leading to paradoxes that make time travel look simple. If you entered one of these regions, you might witness stars being born from supernova remnants or watch your own past unfold in front of you. The catch: you'd never be able to escape to tell the tale, as the time-reversed space would trap you in a causality loop. Here's where science fiction collides with real physics. While Hollywood loves showing characters reversing time to undo disasters, a genuine cosmic reversal wouldn't grant that power. Consciousness relies on entropy. Your brain processes memories because time moves forward. If entropy reversed, your thoughts would unravel backward too, leaving no you to witness the change. The universe might rewind, but there'd be no audience left to watch the replay. The truth is, we don't yet have the physics to answer whether time would flip in a collapse. General relativity allows for it mathematically, but quantum mechanics throws in wild cards. Until we unify these theories, time's fate in a shrinking universe remains one of cosmology's greatest mysteries, one that challenges not just how we see the cosmos, but how we define reality itself. The idea that history repeats itself isn't just a saying. It might be the fundamental nature of reality itself. Long before telescopes or particle colliders, ancient civilizations from the Mayans to Hindu cosmology envisioned time as a circle rather than a straight line, with universes endlessly dying and being reborn. Today, cutting-edge physics is resurrecting this ancient intuition in startlingly precise mathematical form. Take Roger Penrose's conformal cyclic cosmology, a theory where each universe's death becomes the next universe's birth. In this model, when our cosmos contracts into an ultra-dense state, all particles lose their mass through a process called conformal rescaling, effectively hitting a cosmic reset button. What remains isn't nothingness, but a smooth, empty space ready to trigger a new Big Bang, a cosmic phoenix rising from its own ashes. The evidence for such cycles might literally be written in the sky. Penrose and colleagues claim to have found concentric circles in the cosmic microwave background, patterns he calls Hawking points, theorized to be imprints from black hole collisions in a previous universe. These faint thermal fingerprints would be the ultimate cold case, remnants of a cosmos that existed before time as we know it began. Not everyone's convinced, though. Critics argue these patterns could be statistical flukes, cosmic static mistaken for a message from beyond. The Planck satellite's detailed CMB maps haven't conclusively confirmed the circles, leaving the debate hanging in the balance between revolutionary discovery and tantalizing maybe. String theory adds another twist to cyclic models with the ekpyrotic universe scenario. Picture two parallel membranes of higher dimensional space slowly drifting apart in an eternal cosmic dance. When they eventually collide, the impact releases enough energy to mimic a Big Bang, creating a new universe before the branes bounce apart to begin the cycle anew. Unlike traditional cyclic models, this version avoids total collapse altogether. The universe doesn't shrink to a point, it gets reheated through brane collisions, preserving some quantum information across cycles. Some versions even suggest gravitational waves from previous cycles might be detectable, hiding clues in the same ripples of spacetime that LIGO observes from black hole mergers. But cyclic models face formidable challenges. The second law of thermodynamics states entropy always increases, making each cycle more disordered than the last. Over infinite cycles, the universe should have reached maximum chaos by now, a state clearly contradicted by the structured cosmos we inhabit, Penrose's solution. Black holes. As the universe ends, these gravitational monsters consume all matter and energy, then evaporate via Hawking radiation, effectively resetting entropy by scattering it into an infinite void. It's an elegant fix, but one requiring physics beyond our current understanding. The most mind-bending implication: if cycles are real, every possible arrangement of matter must eventually repeat. Somewhere in the chain of universes, an identical version of you might be reading these same words not once, but infinitely many times across eternity. Whether that's comforting or terrifying depends on your perspective. For now, cyclic universe theories remain tantalizing possibilities, their truth hidden in the faintest whispers of cosmic background radiation and the uncharted territories of quantum gravity. As we peer deeper into these mysteries, we're not just studying the universe, we might be uncovering its autobiography, written across countless iterations of existence. String theory rewrites the cosmic rulebook by proposing that our universe isn't alone. It's just one page in an infinite library of parallel realities. Imagine bubbles floating in an endless foam, each bubble a self-contained universe with its own laws of physics, its own timeline, even its own version of gravity. In this sprawling multiverse, the collapse of our cosmos wouldn't be an ultimate ending. It would be a localized event, like a single candle flickering out in a grand hall illuminated by countless others. While galaxies here spiral toward a big crunch, other universes might continue expanding indefinitely, their dark energy burning bright as ours fades. This radical vision stems from string theory's most startling implication: the existence of higher dimensions. Beyond the three spatial dimensions we experience, the math suggests there could be 6 or 7 more, curled up so tightly we'd never notice them. These hidden dimensions might host other universes, separated from ours by less than a millimeter, but in a direction we can't point to. Some models propose these parallel worlds hover just out of reach in a higher dimensional bulk, like sheets of paper stacked in a fourth spatial dimension we can't access. If true, a contraction in our universe might ripple through this bulk, potentially triggering collapses in neighboring realities, or leaving them entirely untouched. The multiverse doesn't just change how we view cosmic collapse, it redefines what reality even means. In an infinite ensemble of universes, every possible outcome must occur somewhere. There could be worlds where dark energy never existed, and gravity won the cosmic tug of war from the start. Others might have already crunched and rebirthed 1,000 times over. The most unsettling possibility: we might live in a Goldilocks zone, universe 1, where conditions just happen to allow stars, planets, and life to emerge, while most others remain barren or blink out of existence too quickly for complexity to arise. Testing these ideas isn't just challenging, it borders on philosophical. If other universes are forever beyond our observational reach, does their existence even qualify as science? Some theorists argue yes, pointing to potential fingerprints of cosmic collisions in the CMB's faintest patterns. Others suggest gravitational wave detectors might one day catch echoes of a neighboring universe's collapse vibrating through higher dimensions. And then there's the wild card: quantum entanglement. If particles in our universe somehow remember interactions with counterparts in other realities, future experiments might uncover subtle anomalies hinting at a larger whole. The multiverse hypothesis forces us to confront humbling questions. If our universe is destined to contract, does its fate matter in a grander scheme where countless others thrive? Or is each reality its own closed story, its collapse as final for its inhabitants as it feels to us? String theory offers no easy answers, only a dizzying glimpse into a cosmos vaster and stranger than we ever imagined, where the rules we take for granted might be nothing more than local ordinances in an infinite cosmic metropolis. The holographic principle turns reality inside out, literally. Imagine the entire universe as a cosmic illusion, a three-dimensional movie projected from information encoded on a distant two-dimensional surface. This isn't just a thought experiment, it's a serious theory with roots in black hole physics. When scientists calculated the maximum entropy a region of space can contain, they found it scales with surface area, not volume. That's like discovering a hard drive stores data based on its case's exterior, not its internal space. If true, everything we perceive, stars, planets, even our own thoughts, might be shadows cast by quantum bits etched on the universe's edge. Now picture that cosmic projector running in reverse. As the universe contracts, the holographic code might begin rewriting itself, erasing information like a celestial tape being rewound. Distant galaxies wouldn't just move closer, they'd pixelate, their fundamental reality degrading as the underlying data transforms. Time itself could emerge from this information flow, meaning a reversal might not just change events but the very framework allowing events to exist. Some versions of this theory suggest the universe isn't just described by information, it is information, a cosmic computation where contraction represents the program executing backward. The implications are dizzying. If the holographic principle holds, a collapsing universe wouldn't just crush matter, it could corrupt reality's source code. Black holes offer a chilling preview. Their event horizons act like cosmic hard drives, storing information about everything they swallow in two-dimensional form. During contraction, the entire universe might resemble a black hole's interior, with space becoming an increasingly glitchy simulation as the holographic framework buckles. Quantum fluctuations could amplify, creating zones where physics itself stutters like a corrupted video file where gravity flickers or light speed changes abruptly. Skeptics argue this veers into philosophy, but the math is surprisingly concrete. The AD/CFT correspondence, a pillar of string theory, explicitly links higher dimensional gravity to lower dimensional quantum fields. It's as if the universe runs on quantum software perfectly mirrored in gravitational hardware, and contraction might force a system reboot. Experiments like Fermilab's holometer have even searched for telltale pixelation in spacetime, though results remain inconclusive. The most radical take: if reality is holographic, its collapse might not be the end. Just as deleting a computer file doesn't destroy the storage medium, a universe's contraction could be the prelude to recompiling reality with new parameters. The same quantum bits might project an entirely different cosmos next time, one where dark energy never existed, or where gravity operates in reverse. We wouldn't just be living in a universe that contracts, we might be living in one that's done so countless times before, each iteration a fresh rendering of the same underlying code. This isn't science fiction, it's the cutting edge of theoretical physics, where the nature of reality itself is up for debate. Whether the holographic principle survives future tests or not, it forces us to confront a profound question. If the universe is information, what happens when the cosmic computer starts backspacing? The answer might rewrite not just our future, but our understanding of existence itself. Detecting a universe in reverse would be like trying to hear a whisper in a hurricane. Right now, every distant galaxy we observe is racing away from us, their light stretched into longer, redder wavelengths, a phenomenon called redshift. If the cosmos began contracting, the first sign would be a subtle shift in that pattern, with faraway galaxies showing less redshift than expected, or even blue shift as they start inching closer. But here's the catch. The universe's vastness means these changes would unfold over billions of years, making them nearly imperceptible within a human lifetime. It's like watching the hour hand of a clock. You know it's moving, but you'd need to stare for ages to see it. Scientists hunt for these clues with tools like the James Webb Space Telescope, which peers deeper into space and further back in time than any instrument before it. By comparing the redshift of ancient galaxies with those closer to us, astronomers can map whether expansion is slowing or reversing. But cosmic dust, measurement errors, and the sheer noise of interstellar space create a minefield of false positives. Imagine trying to detect a single backward step in a crowd of 1 trillion people all running forward. That's the scale of the challenge. Another telltale sign would hide in the cosmic microwave background. Just as the CMB carries imprints of the universe's explosive birth, a contracting cosmos might leave faint fingerprints of its decline. Theorists predict subtle temperature variations or polarization patterns that could signal gravity regaining dominance. Projects like the Simons Observatory in Chile are scanning the CMB with unprecedented precision, searching for these cosmic breadcrumbs. Yet even their data could take decades to interpret conclusively. The most haunting possibility, we might already be seeing hints without realizing it. Some anomalies in supernova brightness measurements, the same data that first revealed dark energy's acceleration, could alternatively suggest expansion is uneven or slowing in patches. Other researchers point to peculiar galaxy cluster movements that don't quite fit the standard model. Are these statistical flukes or the first tremors of a cosmic U-turn? Without better tools, we're like doctors trying to diagnose a patient's fever with a thermometer that only reads hot or cold. Future observatories could change the game. The European Space Agency's Euclid telescope, launched in 2023, is mapping billions of galaxies to trace dark energy's influence with razor-sharp detail. Next-generation gravitational wave detectors might catch ripples from colliding black holes in a contracting universe, whose signatures would differ subtly from those in an expanding one. And quantum sensors buried deep underground could hunt for shifts in fundamental constants like the fine structure constant that might precede spatial collapse. The irony is profound. We're creatures of an instant, living in a universe where change unfolds at a glacial pace. By the time we definitively spot contraction, it might already be unstoppable. Yet that hasn't stopped scientists from turning the cosmos into a forensic crime scene, searching for clues in the light of dying stars, the whispers of relic radiation, and the ghostly pull of dark matter. The answer won't come easily, but if the universe is indeed shrinking, every telescope on Earth is now a detective in the greatest mystery of all time. Right now, every distant galaxy we observe carries a fingerprint of cosmic expansion, their light stretched toward the red end of the spectrum like a siren's pitch dropping as it speeds away. But if the universe ever flipped from expansion to contraction, that redshift would reverse into blueshift, the light of approaching galaxies compressing into higher frequencies like an ambulance siren wailing toward you. It's the universe's equivalent of a car slamming into reverse, a signal so clear it would rewrite astronomy textbooks overnight. The mechanics behind this shift are deceptively simple. When a light source moves away, its waves stretch, sliding toward red. When it approaches, those waves bunch up, skewing blue. Astronomers use this Doppler effect daily, measuring galaxy motions with precision. But here's the catch: cosmic contraction wouldn't announce itself with a sudden, universal blue shift. The first signs would be subtle, a distant galaxy cluster slowing its redshift faster than expected, or a statistical anomaly in supernova data suggesting deceleration. Only over millennia would the trend solidify into a full reversal, with blue shift creeping inward from the cosmic horizon like frost on a window. What would it mean if we spotted this shift? For starters, we'd have to rethink dark energy entirely. Either its repulsive power is fading, or it was never constant to begin with, perhaps a transient phase in the universe's life cycle. Some models suggest dark energy could evolve like a decaying battery, its strength ebbing until gravity takes over. Others propose it's entangled with quantum fields that fluctuate over cosmic timescales. A blue-shifted sky would force us to confront these possibilities head-on, turning theoretical speculation into urgent science. The societal implications are just as staggering. A contracting universe would have a finite expiration date, billions of years perhaps, but an endpoint nonetheless. Entire philosophies and religions have been built on assumptions of cosmic eternity. Their foundations would tremble at the news. Meanwhile, scientists would race to calculate whether contraction spells doom or rebirth. Could the collapse trigger a new Big Bang, as cyclic universe theories suggest? Or would it culminate in a singularity, erasing space-time itself? The answer might determine whether we're living in a one-time universe or a single frame in an infinite cosmic film strip. Yet observing this reversal won't be easy. Light from the universe's edge takes billions of years to reach us, meaning any blue shift we detect would reflect the past, not the present. By the time we see galaxies rushing back, the contraction could already be unstoppable. Future telescopes like the European Space Agency's Euclid or NAS, a Nancy Grace Roman Space Telescope, might catch early hints by mapping galaxy motions with unprecedented precision. But even their data could take decades to interpret conclusively, like hearing the first notes of a symphony played at half speed and trying to guess the finale. The most haunting possibility, blue shift might already be hiding in plain sight. In 2018, astronomers reported a handful of quasars with anomalous redshifts, outliers in the data that some dismissed as measurement errors. Could these be the first whispers of a cosmic turnaround, or just cosmic static? Until we develop tools sensitive enough to separate signal from noise, the universe's trajectory remains a riddle written in light we're still learning to read. One thing's certain: if the sky ever starts turning blue in ways it shouldn't, humanity will face a revelation as profound as Copernicus's. We're not just living in an expanding universe, but one with a rewind button no one knew existed. In a contracting universe, life as we know it would face challenges beyond imagination. Picture a cosmic pressure cooker where the very fabric of reality begins tightening around all existence. As galaxies draw closer together, the night sky would transform from a tranquil starscape into a blazing furnace. Distant suns that once provided gentle starlight would instead loom large and deadly, their combined radiation baking planets that once enjoyed temperate orbits. The increasing density of matter would trigger runaway stellar collisions like bumper cars in slow motion, each impact unleashing bursts of energy capable of sterilizing entire solar systems. But radiation and heat are just the beginning. Space itself would become warped and unpredictable as gravitational forces intensify. Time dilation effects near massive objects would create bizarre pockets where clocks tick at wildly different rates. A planet might experience centuries while its star ages millions of years in the same period. Navigation between worlds would grow perilous as gravitational lensing distorts trajectories, and the very concept of distance becomes fluid. Civilizations that mastered interstellar travel might find their star maps obsolete overnight, with once stable routes now twisted into cosmic knots by the universe's deepening gravity wells. Could intelligence survive these extremes? Some theorists propose radical adaptation strategies. Advanced civilizations might migrate into artificial habitats shielded by technology we can barely conceive. Perhaps structures built inside black hole ergospheres where rotational energy could power cities, or vast megastructures floating between contracting galaxy clusters. Others speculate about uploading consciousness into robust quantum computers capable of enduring extreme conditions, the most far-reaching solution, escaping to another universe entirely. If multiverse theories hold, a sufficiently advanced society might engineer wormholes or dimensional bridges to safer realities, though the energy requirements would dwarf anything humanity has ever produced. Yet these speculations reveal a deeper truth about our cosmic fragility. All life exists at the mercy of forces beyond its control, whether the steady fusion of a star or the mysterious push of dark energy. A contracting universe would simply accelerate timelines we already face, stars burning out, resources dwindling, and environments changing. The difference is one of scale and inevitability. While Earth's biosphere has millions of years before the Sun's death, a collapsing cosmos might impose deadlines measured in mere millennia once contraction reached critical stages. This thought experiment forces us to confront uncomfortable questions about permanence. Every monument, every memory, every scientific achievement rests on the assumption of a stable cosmic stage. But if the curtains of space itself began closing, what would truly last? Perhaps the only enduring legacy would be information patterns of knowledge encoded in light or gravitational waves, cast into the void in hopes that some future intelligence, in some reality, might decipher them. Or perhaps the lesson is more immediate, that in a universe capable of such vast transformations, our time and choices matter precisely because they are fleeting. Whether the cosmos expands forever or eventually reverses course, the present moment remains the only territory we're guaranteed to inhabit, and that makes it infinitely precious. The story of cosmic inflation reads like the universe's greatest magic trick. A fraction of a second after the Big Bang, space itself exploded outward faster than light, smoothing wrinkles in the infant cosmos and setting the stage for everything we see today. But what if that explosive growth wasn't a one-time event? What if it was just one swing of a cosmic pendulum, destined to reverse? Hidden in the fine print of inflation's math lies a tantalizing possibility. The same mechanism that stretched space might someday pull it back. The key lies in the inflaton field, the mysterious energy driver behind inflation's breakneck expansion. Like a coiled spring, this field unleashed pent-up energy to stretch the universe, but some models suggest it could re-energize, flipping from repulsive to attractive gravity. Picture a rubber band snapped taut, then suddenly yanked backward with equal force. the evidence for this reversal might already be hiding in plain sight. When scientists examine the cosmic microwave background, they're seeing a baby picture of the universe just 380,000 years after inflation ended. Those faint temperature variations, the seeds of galaxies, carry subtle imprints of inflation's physics. Some theorists argue certain asymmetries in these patterns could hint at an inflattened field capable of switching directions. It's like finding a receipt in your pocket with half the numbers smudged. You know something was purchased, but the details are tantalizingly incomplete. This isn't just about tweaking equations, it reshapes the origin story of everything. If inflation can reverse, the Big Bang might not have been a beginning, but a rebound. Cyclic models propose our universe is caught in an endless loop: expansion, contraction, and rebirth. Imagine a cosmic accordion, breathing in and out across eons, each compression heating spacetime until it rebounds into a new inflationary epoch. The math behind this is staggeringly elegant. When contraction reaches maximum density, quantum effects could trigger a big bounce, resetting entropy and launching a new cycle with fresh physical constants. Yet the challenges are as profound as the possibilities. Why didn't previous cycles erase all structure, leaving behind a featureless void? Some theorists point to dark matter's gravitational scaffolding as a possible survivor between cycles, while others suggest quantum information might tunnel through singularities intact. Skeptics counter that we've never observed evidence of pre-Big Bang events, but supporters argue such evidence would be scrambled beyond recognition in each rebirth, like a cassette tape played through a supernova. The most mind-bending implication: if inflation is reversible, our universe might be riding the crest of a wave that's destined to crash. The same forces that crafted galaxies could one day dismantle them, not with a bang, but with a cosmic sigh, a deflation so gradual that stars might not notice until their light can no longer escape the gathering pull. Whether inflation's story ends with a period, an exclamation point, or an ellipsis remains one of cosmology's greatest open questions, and the answer might rewrite not just our future but our past. Einstein once scribbled a small term in his equations, lambda, the cosmological constant, to balance the universe against gravity's relentless pull. At the time, astronomers believed the cosmos was static, neither expanding nor contracting, and Einstein's adjustment kept it mathematically steady. But when Edwin Hubble revealed the universe was actually stretching apart, Einstein famously dismissed the constant as his greatest blunder. Little did he know that same term would return to haunt cosmology a century later, not as a mistake, but as a prophetic clue to dark energy's existence. Now, physicists are asking an even wilder question. If lambda could explain cosmic acceleration, might it also predict a reversal? The irony is thick enough to cut with a knife. The very idea Einstein abandoned now dominates modern cosmology, repurposed to describe dark energy's repulsive force, but the story doesn't end there. Revised versions of his equations suggest lambda could be dynamic, a value that changes over time, flipping from pushing space apart to pulling it back together. Picture a pendulum swinging between expansion and contraction, with a cosmological constant as the hidden hand controlling its arc. Some models propose lambda isn't a constant at all, but a field that decays or interacts with other forces, like a dial that could someday turn gravity back into the universe's dominant player. General relativity, Einstein's magnum opus, doesn't just describe space and time. It weaves them into a single fabric that bends and warps under the influence of matter and energy. In an expanding universe, this fabric stretches like taffy, galaxies drifting apart as new space emerges between them. But relativity also allows for the opposite, a cosmic contraction where space-time crumples inward, dragging galaxies toward a shared fate. The equations are agnostic. They don't care which direction the universe goes, only that it obeys the balance between matter, energy, and geometry. Here's where things get eerie. If dark energy weakens enough, relativity predicts gravity would begin stitching the universe back together. Distant galaxies would slow their retreat, halt, and then plunge toward one another in a mirror image of the Big Bang's outward rush. Time itself would behave differently in this collapsing cosmos. Clocks near massive objects would tick ever slower compared to those in emptier regions, creating pockets where causality twists into knots. The universe's end might not be a single moment, but a fractured, asynchronous unraveling. Yet relativity alone can't answer whether this reversal is inevitable. For that, we need quantum physics, a realm Einstein famously resisted. Modern theories attempt to marry the two, suggesting lambda might emerge from quantum fluctuations in hidden dimensions or vacuum energy. If so, the cosmological constant could be less like a dial and more like a quantum switch capable of unpredictable jumps. The same physics that birthed the universe might one day reclaim it, with Einstein's blunder standing at the center of it all, a mathematical specter that refuses to fade, quietly shaping cosmic destiny from beyond the grave. The takeaway: even geniuses underestimate their own insights. Einstein's lambda was never a blunder, just an idea ahead of its time, waiting for the universe to reveal its next act. As we peer into the abyss of dark energy and cosmic fate, his equations remain our most reliable map, hinting at turns in the road even their creator couldn't foresee. The question now isn't whether relativity holds the key to contraction, but whether we're bold enough to turn it. Einstein's theory of general relativity paints the universe as a cosmic trampoline, where matter and energy bend the fabric of spacetime, and the shape of that bend determines everything from the orbit of planets to the fate of the cosmos itself. One of its most startling predictions: the universe could be closed, a vast but finite bubble where space eventually curves back on itself like the surface of a four-dimensional sphere. In this scenario, if the total density of matter and energy exceeds a critical threshold, roughly 5 atoms per cubic meter, gravity's relentless pull would overcome dark energy's push, sending galaxies spiraling back toward each other in a slow-motion collapse. It's a cosmic game of tug-of-war where the rope is spacetime itself, and the outcome hinges on a razor-thin balance we're still struggling to measure. Current observations hover right at this knife edge. Satellite measurements of the cosmic microwave background suggest the universe's geometry is flat to within a 1% margin of error, but flat doesn't necessarily mean infinite. Imagine a sheet of paper so vast, its curvature is imperceptible to an ant crawling across it. Our observable cosmos might be a tiny patch of a much larger closed universe, with gravity's grip strengthening over scales we can't yet see. The Planck satellite's data even contains a faint anomaly, slightly more gravitational lensing of the CMB than expected, as if space has a subtle curvature tugging at light rays. Could this be the first hint that we're living in a cosmic bubble destined to pop? The math behind this is both elegant and haunting. In a closed universe, Einstein's equations demand that expansion eventually halts and reverses, like a ball thrown upward, slowing at its peak before plummeting back to Earth. The critical factor is omega, the ratio of the universe's actual density to that make-or-break threshold. If omega is greater than 1, collapse is inevitable. Current estimates place omega at almost exactly 1, but with error bars that leave room for either a whisper-thin margin above or below. It's like standing on a scale that reads 99.9 pounds when 100 triggers an alarm. We're left wondering if the next snack will tip us over. What's fascinating is how this cosmological uncertainty echoes through history. When Einstein first proposed a closed universe, astronomers believed the cosmos was static and eternal. Today, we know it's dynamic, but the question of its shape, and thus its fate, remains open. Future telescopes like the Vera Rubin Observatory could settle the debate by mapping the distribution of galaxies with unprecedented precision, revealing weather space curves on scales larger than we've probed. Until then, we're left with a tantalizing possibility. The universe might not just be expanding, but winding up like a spring, storing the energy for a reversal we won't see coming until the stars themselves start falling back toward us. Phantom energy isn't just another form of dark energy, it's dark energy on steroids, a hypothetical variant so extreme it makes the universe's current expansion seem leisurely. Unlike ordinary dark energy, which pushes galaxies apart at a steady pace, phantom energy grows stronger over time, its repulsive force spiraling out of control until even atoms can't hold themselves together. Picture a car accelerating faster with every second. First it outruns bicycles, then jets, then light itself, until the vehicle's own structure disintegrates from the stress. That's phantom energy's endgame, a cosmic demolition so thorough it's been dubbed the Big Rip, where galaxies, stars, and even subatomic particles are shredded by the unrelenting expansion of space itself. Yet there's a bizarre twist buried in the equations. Some theoretical models suggest phantom energy might not be a one-way ticket to oblivion. Under certain conditions, this same apocalyptic force could flip its own script, transforming from an unstoppable repulsive power into an irresistible gravitational pull. It's as if the universe's gas pedal suddenly became its brake, sending expansion into reverse. How the key lies in phantom energy's relationship with quantum fields. Most dark energy models treat it as a static background force, like a canvas stretching uniformly beneath the cosmos. But phantom energy could be dynamic, a field that evolves, interacts, or even decays. Imagine a spring compressed to its limit. At some critical threshold, the energy stored might rebound inward with equal ferocity. In cosmic terms, that rebound could switch the universe from accelerating expansion to runaway contraction. This duality makes phantom energy the ultimate wild card in cosmology's deck. On one hand, it could deliver the most violent fate imaginable, a big rip so absolute it leaves no structure intact, not even space-time itself. On the other, it might be the hidden mechanism that resets the cosmic clock, triggering a contraction that births a new universe from the ashes. The difference hinges on phantom energy's equation of state, a term physicists use to describe how its pressure relates to its density. If the pressure becomes negative enough, it crosses a threshold where repulsion turns to attraction, like a magnet reversing polarity. The math allows for this switch, but the trigger remains unknown. Could it be tied to the universe's temperature dropping below a critical level, or an interaction with undiscovered particles lurking in the quantum foam? What's truly unsettling is how little warning we'd have. Phantom energy's effects would be stealthy until they weren't, like a bridge corroding invisibly until one day it collapses without a sound. Current telescopes might spot subtle clues in the redshift of supernova or anomalies in galaxy cluster motions, but by the time the trend became undeniable, the universe's fate could already be sealed. Some theorists argue we should be searching for phantom echoes in gravitational wave data, while others propose tabletop experiments to simulate phantom energy's behavior in quantum systems. The stakes couldn't be higher. If phantom energy exists and flips to contraction, it wouldn't just change the universe's trajectory, it would rewrite the rules of the game. The same quantum weirdness that might trigger the switch could alter fundamental constants mid-collapse, tweaking gravity's strength or the speed of light in ways that make the cosmos unrecognizable. Stars formed in such a universe might burn different fuels, chemistry could obey new laws, and life, if it emerged at all, might take forms beyond our imagination. Phantom energy isn't just a cosmic threat or a salvation. It's a reminder that the universe's deepest secrets might still be hiding in plain sight, masquerading as mathematical curiosities until the moment they rewrite reality itself. Brain collisions might sound like something from a far-fetched sci-fi novel, but in the realm of string theory, they're a legitimate possibility, one that could rewrite the fate of our entire cosmos. Picture our universe not as an isolated bubble floating in nothingness, but as a vast multidimensional membrane, or brain for short, drifting through a higher dimensional space called the bulk. These brains aren't just theoretical scribbles on a chalkboard. They're dynamic structures vibrating and moving through dimensions beyond our perception. And if two of them collide, the energy released could be enough to reset reality itself, sparking a new Big Bang or even reversing our universe's expansion in a cosmic game of bumper cars. This idea, known as the ekpyrotic universe scenario, turns the traditional Big Bang narrative on its head. Instead of a singular explosion from nothingness, our universe might be the aftermath of a colossal brain collision, a rebound from a previous cosmic cycle. Think of it like two sheets of paper smashing together in a fourth spatial dimension we can't see. The impact wouldn't just create heat and light. It could stretch and compress space-time, triggering either a new inflationary epoch or a contraction phase that pulls everything back toward a singularity. The wildest part, this process might not be a one-time event. If brains oscillate through the bulk, they could collide, separate, and collide again in an endless loop, birthing universes in a cycle that never truly begins or ends. But how would such a collision affect us? If another brain were on a collision course with ours, the first signs might be subtle, tiny ripples in the fabric of space-time, detectable only by the most sensitive gravitational wave observatories. As the brains drew closer, the laws of physics could start to warp. Fundamental constants like the speed of light or the strength of gravity might fluctuate, creating regions where matter behaves unpredictably. Stars could flicker like candles in a draft, their nuclear fusion processes disrupted by encroaching higher dimensional forces. By the time the collision itself occurred, the universe as we know it might already be unrecognizable, its structure reshaped by energies beyond our current comprehension. The implications stretch even further if our brain isn't alone. Some models suggest the bulk could be teeming with other brains, each hosting its own universe with different physical laws. A collision might not just reset our cosmos, it could merge it with another, blending dimensions and rewriting reality in ways that defy imagination. Imagine two soap bubbles merging into one, their surfaces rippling and reforming into a new, unified shape. Now scale that up to universes where the surface is all of space-time, and the ripples are the birth and death of galaxies. Skeptics argue that brain cosmology is untestable, a beautiful idea trapped in the realm of mathematical elegance without observable proof. But supporters point to potential fingerprints in the cosmic microwave background, unexplained anomalies that could hint at pre-Big Bang events. Others suggest that high-energy particle colliders might, by sheer accident, create microscopic black holes or other phenomena that reveal hidden dimensions. It's a long shot, but in a field where the universe keeps surprising us, even the wildest ideas deserve a seat at the table. At its core, the brain collision hypothesis forces us to confront a humbling truth. The universe might be far stranger than we've dared to imagine. Whether it's a one-time event or part of an infinite cycle, the possibility that our reality is just one membrane in a higher dimensional sea reshapes not just cosmology, but our place within it. If brains can collide, then the cosmos isn't just expanding or contracting, it's dancing, and every collision is a step in a routine we're only beginning to learn. The arrow of time isn't just a metaphor, it's woven into the universe's very fabric through thermodynamics, where entropy dictates that disorder always increases. Right now, as galaxies drift apart and stars burn out, the cosmos marches toward maximum chaos like a sandcastle slowly crumbling in the tide. But flip the script to a contracting universe, and thermodynamics enters uncharted territory. Suddenly, entropy could decrease like scattered puzzle pieces sliding back into place. Imagine spilled milk flowing upward into its glass, shattered china reassembling on the table, or smoke particles retreating into a cigarette. These everyday impossibilities might become cosmic inevitabilities as time's arrow flips direction. This reversal wouldn't just affect objects, it would rewrite physics at its core. Take black holes, those cosmic vacuum cleaners that devour matter and information. In an expanding universe, they grow by swallowing entropy, their event horizons stretching to contain the disorder. But in contraction, they might vomit it back out, unraveling into perfect spheres of low-entropy plasma as gravity weakens its grip. Even quantum mechanics would turn strange. Particles that once popped in and out of existence unpredictably might begin moving in lockstep, like a film of boiling water played in reverse where bubbles shrink obediently back to their source. The implications for life are staggering. Consciousness itself relies on increasing entropy. Your brain processes memories because time flows forward, creating new neural pathways. Reverse the arrow and thoughts would unwind like yarn from a sweater, erasing experiences before they're formed. Civilizations might rise and fall in reverse, their technologies simplifying rather than advancing, until fire becomes unlearned and language dissolves into primal sounds. Some theorists argue this is why we don't observe time running backward now, because sentient beings can only exist in the entropy-increasing phase, making us inevitable products of expansion. Yet there's a catch. Thermodynamics might find loopholes in collapse. While classical physics says entropy must decrease when the universe shrinks, quantum gravity introduces wild cards. Black hole evaporation via Hawking radiation suggests information, and thus entropy might be preserved even in extreme conditions. String theory proposes hidden dimensions could store entropy like a cosmic backup drive, preventing true reversal. And if the universe bounces rather than crunches, entropy could reset entirely at the moment of rebound, like shuffling a brand new deck of cards after the old one's been dealt. The ultimate irony, we may never know if time reverses because by the time it happened, cognition itself would unravel. Like a detective solving a crime only to forget the clues, any observer in a contracting cosmos would lose the ability to document the change as their neurons unpair. Our only hope of glimpsing this thermodynamic twilight lies in advanced simulations or subtle anomalies in the cosmic microwave background, faint echoes of a universe that once knew which way time flowed before physics itself forgot. Quantum gravity is the holy grail of modern physics, a theory that could finally unite the bizarre rules of the quantum world with the cosmic scale predictions of general relativity. Right now, these two frameworks describe reality with astonishing precision, but they speak completely different languages. Quantum mechanics deals in probabilities and particles, while general relativity paints spacetime as a smooth, bendable fabric. When these worlds collide, like at the center of a black hole or the instant of the Big Bang, the math explodes into infinities and our understanding crumbles. This isn't just an academic puzzle, it's the barrier standing between us and the answer to one of cosmology's biggest questions. Could the universe truly reverse its expansion? Picture trying to predict the path of a hurricane using Newton's laws alone. It might give you a rough idea, but without fluid dynamics and thermodynamics, you'll miss crucial details. Similarly, without quantum gravity, our models of cosmic contraction are like weather forecasts without atmospheric science. Take the Big Crunch. General relativity predicts matter collapsing into a singularity of infinite density, but quantum effects at those scales would likely prevent such extremes. Some theories suggest particles might reach a smallest possible size, like pixels on a cosmic screen, creating an energetic rebound instead of a collapse. Others propose spacetime itself becomes foamy and chaotic, with wormholes or quantum tunnels opening new escape routes for matter and energy. The stakes couldn't be higher. If quantum gravity allows for a bounce rather than a crunch, the universe might not end, it could recycle. Loop quantum cosmology, a leading candidate theory, replaces the singularity with a quantum bridge, where spacetime repels itself at high densities, launching a new inflationary epoch. String theory offers another twist. Collapsing universes might shed dimensions as they shrink, rebooting with fewer spatial axes than our familiar three. Even more radical is causal dynamical triangulation, where spacetime is built from tiny geometric chunks that reconfigure during contraction, potentially altering fundamental constants in the process. Experimental clues are frustratingly scarce but not absent. The afterglow of the Big Bang might hide signatures of quantum gravity, subtle statistical anomalies in the cosmic microwave background's temperature fluctuations. Gravitational wave observatories could one day detect echoes from the very early universe, ripples that interacted with quantum spacetime foam. Tabletop experiments with supercooled atoms or superconducting materials are simulating how spacetime might behave at microscopic scales, offering indirect glimpses into physics we can't yet probe directly. What's clear is this: until we crack quantum gravity, the universe's fate hangs in a tantalizing limbo. Will contraction remain a theoretical curiosity, or will new physics reveal it as an inevitable chapter in cosmic history? The answer might rewrite not just our future, but our past, turning the Big Bang from a beginning into a turning point in an infinite cycle of expansion and rebirth. The equations we're missing could be the key to it all, hiding in plain sight, waiting for the next Einstein to piece them together. Supercomputers are building universes in their circuits, not in some distant future, but right now. Behind the unassuming walls of research labs, machines like NASA, Pleiades, or Japan's Fugaku are crunching numbers at speeds unimaginable just decades ago, simulating cosmic collapse with a precision that would make Einstein's head spin. These aren't just video game renderings, they're mathematical mirrors of reality, where every galaxy, every particle, even the fabric of spacetime itself, is represented by equations dancing in perfect sync. Scientists feed these digital realms with our best guesses about dark energy's behavior, gravity's pull, and the quantum quirks of matter, then hit play to watch universes live, die, and sometimes reverse course before their eyes. The results are equal parts enlightening and unsettling. One groundbreaking simulation from the University of Geneva modeled dark energy as a decaying field, its repulsive strength ebbing over billions of virtual years. At first, the digital cosmos expanded just like our galaxies racing apart, their light redshifting into oblivion. But then, around the simulation's equivalent of 50 billion years from now, something extraordinary happened. The galaxies slowed like cars coasting to a stop on an empty highway. Then, almost imperceptibly at first, they began moving toward each other again, their light blue shifting as space itself started shrinking. The simulation didn't just predict a collapse, it showed how eerily quiet the turnaround could be, with no fanfare to mark the universe's change of heart. Other simulations explore darker possibilities. A team at Harvard tweaked dark energy into its most extreme form, phantom energy, and watched their virtual universe tear itself apart in a big rip. But here's the twist: when they adjusted quantum parameters to allow energy decay, the rip didn't end in oblivion. Instead, the shredded remnants of spacetime recoiled, collapsing into a singularity that promptly bounced into a new inflationary epoch. It was as if the universe had performed a cosmic judo move, using its own destructive momentum to flip into rebirth. These digital experiments suggest that even the most violent ends might be gateways, not finales. The devil, of course, is in the data. Simulations are only as good as their assumptions, and dark energy remains the ultimate wild card. Some models treat it as a constant force, like Einstein's cosmological lambda. Others simulate it as a dynamic field that interacts with dark matter or even hypothetical particles from extra dimensions. Each variation spins the digital cosmos toward different fates, some ending in icy isolation, others in fiery rebirth. The most intriguing runs come from teams incorporating quantum gravity effects, where the fabric of spacetime itself becomes granular at tiny scales. In these scenarios, contraction doesn't lead to a singularity, but to a quantum foam where the universe reorganizes its fundamental rules before bouncing back. What emerges from all these simulations is a humbling truth. The universe's fate isn't just about forces and matter, but about how those pieces interact in ways we're still deciphering. Like meteorologists predicting a storm's path, cosmologists must account for countless variables, some known, some guessed, some still hidden in the cosmic fog. Every new simulation refines the picture, but also reveals new questions. Do quantum fluctuations during contraction spawn strange new particles? Could gravitational waves from collapsing galaxy clusters carry signatures of impending reversal? The answers might be hiding in the next generation of supercomputers, where universes yet unborn wait patiently in lines of code, ready to test our boldest theories about how it all ends or begins again. A universe that expands and contracts like a cosmic lung forces us to rethink everything we assume about meaning and existence. If every Big Bang is just the latest in an endless series, then every civilization, every star, every thought that ever existed will eventually be compressed into a singularity, only to be reborn and play out again in nearly identical form. This cyclical view of time isn't new. Ancient Hindu texts spoke of universes breathing in and out over trillions of years, but modern physics gives the idea teeth, transforming poetic metaphor into mathematical possibility. The stakes are dizzying. If the cosmos is on repeat, are our choices truly ours or just echoes of infinite past iterations? Consider the concept of progress, the bedrock of modern science and culture. We celebrate technological leaps and moral evolution, assuming humanity marches toward something greater. But in a cyclical universe, every innovation, every hard-won lesson would be erased in the crunch, only to be rediscovered afresh in the next cycle. History becomes less a ladder and more a treadmill, with each epoch's triumphs destined for reset. Some philosophers argue this negates meaning entirely. If nothing endures, why strive? Others counter that meaning isn't found in permanence, but in the quality of each moment, like a sunset, no less breathtaking because it's fleeting. The psychological weight of contraction would reshape human ambition. Imagine a society that knows its art, its discoveries, even its collective memory will one day unravel like a knit sweater pulled at the seams. Would we still build cathedrals, write symphonies, or launch probes to the stars? Or would we turn inward, prioritizing transient experiences over lasting legacies? Cultures that embraced cyclical time, like the Maya or ancient Buddhists, often focused on spiritual enlightenment over material accumulation, seeing liberation from the wheel of rebirth as life's ultimate goal. A modern civilization facing cosmic collapse might undergo a similar reckoning, trading exponential growth for existential depth. Yet there's a paradoxical comfort in cyclicity. If the universe reboots, then no mistake is final, no extinction permanent. Every cosmic death plants the seed for new beginnings, offering a form of immortality through recurrence. Nietzsche's concept of eternal return, the idea that we'll relive our lives identically, infinitely, takes on new urgency in this light. Would knowledge of the cycle make us live more deliberately, knowing our actions ripple across incarnations? Or would it breed nihilism, a sense that nothing ultimately matters? The deepest tension lies between physics and phenomenology, what the equations say versus what consciousness experiences. Even if the universe is trapped in an endless loop, we only perceive time's arrow moving forward. Our joys and struggles feel real precisely because we can't remember past cycles or foresee future ones. In that narrow slice of perceived existence, meaning isn't handed down by the cosmos. It's built through choices, relationships, and the stories we tell. The irony: a collapsing universe might strip life of eternal significance, but in doing so, it could amplify the value of the present, the only moment we're ever guaranteed to inhabit. Perhaps the answer isn't in resisting the cycle, but redefining what meaning entails. If the cosmos forgets, that doesn't erase the beauty of a Bach fugue or the courage of a child's first step. Like sand mandalas painstakingly crafted only to be swept away, our impermanence doesn't negate our artistry, it sharpens it. The universe may not care about our lives, but that very indifference is what makes our capacity to care so extraordinary. In the face of Contraction's void, our stubborn insistence on finding purpose might be the most rebellious, most human act of all. Long before telescopes or particle accelerators, humanity's oldest stories whispered of universes that breathe, expanding and contracting in grand, rhythmic cycles. Hindu texts describe Brahma's cosmic day and night, where creation unfolds for billions of years before dissolving into primal waters, only to rise again. The Norse spoke of Ragnarok, an apocalyptic battle that destroys the world, yet leaves fertile soil for new life. Even indigenous Australian Dreamtime stories tell of ancestral spirits shaping the world in iterative acts of creation. These aren't just colorful myths, they're uncanny premonitions of modern cosmology's most daring theories, as if ancient cultures glimpsed the universe's heartbeat millennia before science caught up. Take the Hindu concept of Kalpa, a single cycle of creation and destruction lasting 4.32 billion years, a number eerily close to Earth's actual age. The Puranas describe universes layered like lotus petals, each with its own laws and timelines, mirroring today's multiverse hypotheses. The Maya calculated cosmic cycles with precision, their long count calendar tracking epochs that reset like a celestial odometer. What's striking isn't just the accuracy of these metaphors, but their visceral understanding of time as cyclical rather than linear, a perspective that Einstein's equations now echo in models like conformal cyclic cosmology. The parallels grow deeper when examining destruction myths. Norse legends foretold stars plunging into the sea, and the sky itself cracking apart, images that uncomfortably resemble the Big Crunch's collapsing galaxies or the Big Rip's shredded spacetime. The Buddhist concept of samsara, an endless wheel of death and rebirth, finds a scientific cousin in Penrose's CCC theory, where black hole collisions in one universe seed the next. Even the biblical apocalypse, with its promise of a new heaven and new earth, aligns with quantum bounce models where contraction births fresh cosmic epochs. Why do these echoes persist across epochs and continents? Some scholars argue its archetypal human minds instinctively pattern reality as cycles, from seasons to lifespans. Others propose more radical explanations. Could oral traditions preserve fragmented knowledge of ancient civilizations that somehow deduced cosmic truths? Or might there be an intuitive grasp of universal principles encoded in our collective unconscious? The Aztecs believed 5 suns had already risen and fallen before theirs, a number coincidentally close to physicists' estimates of how many times entropy might allow universe recycling before total heat death. Yet the differences between myth and science are as revealing as the similarities. Ancient visions often tied cosmic cycles to moral narratives. Ragnarok's destruction stemmed from Loki's treachery, while Hindu dissolution is a return to divine unity. Modern physics, by contrast, offers no judgment, only equations. Still, the overlap raises provocative questions. If cultures separated by millennia and geography independently envisioned cyclical universes, could that hint at an underlying truth our instruments haven't yet quantified? Or is it simply that staring into the night sky invites certain universal ponderings, whether around a campfire or in a quantum lab? Perhaps the most humbling lesson lies in temporality itself. The Hopi spoke of worlds rising and crumbling like waves, a view that resonates with brain collision theories. The ancient Egyptians saw time as a spiral, where events recur but never identically, much like loop quantum cosmology's evolving cycles. These narratives remind us that our cutting-edge cosmology might be rediscovering what intuitive minds once knew, that the universe is less a clock winding down than a phoenix, forever dying to be reborn. As we peer through telescopes at redshifted galaxies, we're not just doing science, we're joining a conversation that began when the first human looked up and wondered if the stars remember their past lives. Even with our most powerful telescopes and supercomputers, predicting the universe's ultimate fate is like trying to forecast the weather on a planet we've never seen. The equations might be elegant, the simulations breathtaking, but they're built on foundations of known unknowns and worse, unknown unknowns. Take dark energy, the phantom force driving cosmic acceleration. We've measured its effects, but we still don't know what it is. Is it a constant force woven into space itself, as Einstein's cosmological constant suggests? Or is it a dynamic field that could decay, fluctuate, or even reverse course tomorrow? The difference isn't academic, it's the gap between a universe that expands forever and one that eventually turns inward like a collapsing souffle. The problem isn't just missing data, it's the sheer scale of the cosmic experiment we're trying to decipher. Imagine watching a single frame of a movie and trying to guess the ending. That's essentially our position. We've observed a fraction of the universe's lifespan, and even that glimpse is blurred by the limits of light's finite speed. The most distant galaxies we see are snapshots from billions of years ago, their current state forever hidden by the expanding void between us. To predict contraction, we'd need to track dark energy's behavior over timescales far beyond human history, a task as daunting as guessing the trajectory of a single atom in a hurricane. Then there's the elephant in the room, quantum gravity. Our two most successful theories, general relativity and quantum mechanics, become gibberish when pushed to the extremes of black holes or the Big Bang's first moments. Without a unified theory, we're left guessing how space-time behaves at the densities contraction would produce. Will quantum effects create a bounce, as loop quantum cosmology suggests? Or will relativity's singularities hold sway, crushing all matter into an infinitely dense point? Until we bridge this theoretical chasm, our collapse scenarios are little more than educated fan fiction. Even if we crack these puzzles, the universe might hide its cards forever. Some models suggest dark energy's evolution is so slow that observable changes would take hundreds of billions of years, far longer than stars will keep shining. Others propose that contraction's early signs, like anomalous galaxy motions, could be statistically indistinguishable from cosmic variants. It's like listening for a whisper in a thunderstorm. The signal might be there, but noise drowns it out. Future telescopes like the ESA's Euclid or NAS, a Roman space telescope, will sharpen our view, but they're still peering through a keyhole at a room we've never entered. The irony is delicious. We live in an age where we've mapped the cosmic microwave background to within a hair's breadth, where gravitational wave astronomy lets us hear black holes colliding a billion light years away, yet the universe's ultimate fate might remain stubbornly out of reach. Not for lack of trying, but because some answers are written in invisible ink or in a language we haven't yet deciphered. The quest isn't futile, though. Every dead end in cosmology has a way of circling back as a breakthrough. Einstein's blunder became dark energy's cornerstone. Quantum weirdness birthed the silicon chip. However the story ends, the universe has a knack for surprises, and that in itself is a kind of revelation. If the universe's collapse wasn't just a theoretical possibility but an inevitable certainty, humanity would face an ethical dilemma of cosmic proportions. Should we pour our collective resources into preparing for an event billions of years away? On one hand, the idea of cosmic doomsday prepping seems absurd when measured against immediate crises like climate change or global conflicts, but zoom out far enough and the survival of consciousness itself might hang in the balance. Some philosophers argue that advanced civilizations have a moral imperative to become cosmic gardeners, cultivating life even in the face of universal decay. Others counter that diverting effort toward hypothetical futures borders on negligence when present suffering demands action. Consider the practicalities. Building self-sustaining arcs, whether generation ships, artificial habitats, or digital consciousness backups, would require centuries of coordinated effort. The Breakthrough Starshot initiative, aiming to send nanocraft to Alpha Centauri, shows we're already flirting with multi-generational projects. But escaping a contracting universe wouldn't just mean relocating. It might demand rewriting physics itself. Some theories suggest creating baby universes in laboratories by manipulating quantum fields, a feat that makes nuclear fusion look like child's play. Even if possible, the energy costs could starve entire sectors of Earth's economy, raising dystopian questions about who gets saved when resources are finite. The ethical framework split dramatically. Utilitarians might calculate that ensuring trillions of future lives outweighs current sacrifices. Yet virtue ethicists warn that obsessing over distant survival could erode the very values worth preserving, like empathy and community. Indigenous cosmologies offer a counterpoint. Many traditions emphasize harmony with natural cycles over domination, suggesting acceptance rather than resistance might be the wiser path. And then there's the haunting Fermi paradox angle. If intelligent life commonly tries to escape cosmic doom, where is everyone? Their absence could be a silent warning that such efforts are doomed. Perhaps the most unsettling question isn't whether we can prepare, but whether we should. A civilization fixated on outlasting the universe might neglect the beauty and meaning found in transience, the way a cherry blossom's value stems from its fleeting bloom. Alternatively, our drive to survive against impossible odds may be what ultimately defines us. As the philosopher Anders Sandberg notes, the universe doesn't owe us meaning, but we can owe it to ourselves to create some. Whether that means building arcs or simply bearing witness to the cosmos' final moments, remains the greatest debate we may never have to face, but the act of considering it already reshapes how we value our fragile, fleeting present. Hollywood loves a good apocalypse: asteroids hurtling toward Earth, zombies overrunning cities, or the sun ballooning into a red giant by next Tuesday. But when it comes to the big crunch, pop culture has gotten the timeline catastrophically wrong. Blockbusters often depict cosmic collapse as an overnight catastrophe, with panicked news anchors counting down to doomsday as stars blink out in real time. The reality: if the universe reverses course, the process would unfold over tens of billions of years, a timescale so vast dinosaurs roamed Earth closer to our present day than our present is to Contraction's hypothetical start. This isn't just pedantic nitpicking. Misunderstanding cosmic timelines warps public perception of real scientific risks. When people hear the universe could collapse, they imagine an existential threat to their grandchildren, not a distant event so far in the future that all stars will have burned out long before. Astronomer Carl Sagan famously visualized cosmic history as a single cosmic calendar, where all human existence occupies the last few seconds of December 31st. On that scale, contraction wouldn't begin until deep into a hypothetical second calendar, a reminder that cosmic processes operate on a stage where mountains rise and erode in the blink of an eye. Communicating these scales requires creative storytelling. Scientists at NASA, a jet propulsion laboratory, once illustrated it by comparing light's journey across the observable universe to a cross-country road trip. If the Milky Way were the size of a coffee cup, the visible cosmos would stretch from New York to Los Angeles, with contraction barely moving the needle on the odometer for eons. Others use geological metaphors. Just as plate tectonics reshapes continents imperceptibly over millennia, cosmic contraction would be a slow-motion rearrangement of the heavens, invisible to any single civilization. Yet some misconceptions stem from legitimate scientific ambiguity. Early media coverage of dark energy often framed it as a countdown to collapse, borrowing language from thermodynamics about unstable systems. Modern cosmology recognizes dark energy as far more nuanced. It could be constant, decay, or even fluctuate like the stock market. This complexity rarely makes the news, leaving audiences with outdated analogies of cosmic springs recoiling or pendulums swinging back. The truth is messier. Contraction isn't inevitable, and if it happens, it might not resemble anything in our physics textbooks. Breaking through these myths matters beyond astronomy classrooms. When people grasp the true scale of cosmic events, they gain perspective on humanity's fleeting yet extraordinary moment in the spotlight. Our civilization arose during a golden window, after the primordial fires cooled but before the stars fade, a sliver of cosmic time where questions about the universe's fate can even be asked. That's a story far more compelling than doomsday sensationalism, and one worth telling right. The idea that the universe could reverse its expansion and shrink again is more than a scientific hypothesis. It's a mirror held up to our deepest questions about reality. For centuries, humans have gazed at the stars and wondered if the cosmos had a beginning, an end, or simply cycles we can't yet comprehend. Modern cosmology hasn't settled the debate, but it's given us tools to explore possibilities that would have been unthinkable to earlier generations. Whether the universe contracts in a fiery big crunch, fades into icy darkness, or bounces into a new existence, each scenario forces us to confront the fragility and grandeur of our place in the cosmic story. Consider the stakes. If the cosmos is truly on a collision course with itself, then every galaxy, every planet, every life form is part of a narrative with an expiration date. But here's the twist: that very impermanence might be what gives existence its meaning. Like a sandcastle built knowing the tide will eventually wash it away, the universe's potential finitude sharpens the beauty of its transient moments. The stars burning brightly against the void, the delicate balance that allows life to flourish, even our ability to ponder these mysteries, they all gain poignancy when framed against the possibility of an ultimate end. Yet the science remains tantalizingly open-ended. Dark energy's true nature, the quantum underpinnings of gravity, and the fabric of space-time itself are still puzzles with missing pieces. Every new telescope, every advanced simulation, and every theoretical breakthrough brings us closer to answers, but the universe guards its secrets well. What's remarkable isn't just the diversity of possible outcomes, fire or ice, rebirth or oblivion, but the fact that we've developed the capacity to imagine them at all. In a cosmos that may forget itself with each cycle, our curiosity becomes a fleeting spark of awareness, a brief window where the universe contemplates its own fate. This is why the question of cosmic contraction transcends astronomy. It's a bridge between the empirical and the existential, a reminder that the universe isn't just something we observe, but something we inhabit, shaped by forces we're only beginning to decode. Whether you're a scientist scrutinizing redshift data or someone who simply marvels at the night sky, the mystery unites us in shared wonder. The cosmos may or may not reverse its expansion, but our journey to understand it is its own kind of rebellion against the dark, a testament to the human spirit's refusal to stop asking, what if? So as we close this chapter, remember, the universe's story is still being written, and we're privileged to live in an era where we can read its pages. If you've enjoyed this voyage to the edge of known science, there's plenty more to explore. Like and subscribe to join us on the next adventure, where we'll keep unraveling the cosmos' greatest enigmas. Until then, keep looking up, not just to see the stars, but to glimpse the infinite questions they still hold. The night sky isn't just a sight, it's an invitation